like if this epsilon is not a function of sigma alpha. This is one thing that I explained. So epsilon is a constant. Okay. It means, and epsilon is my gauge parameter. You know, the gauge parameter, it generates the gauge symmetries of the theory, and these are the gauge symmetries of the theory here. Okay. And also, in the passing, I might mention that in our theory here, we have only one epsilon. We are lucky. But it means, if you do supersymmetry in details, you talk about n equal to 1, n equal to 2, n equal to 4, n equal to these supersymmetries. What it really means practically for us, we would not have that much time to go into. First, I was thinking of developing several lectures on supersymmetry, but we don't have that much time. Life is finite. We have to finish a particular thing in a particular given amount of time. So, if your theory has only one epsilon, we understand by it that we are working with capital N equal to 1 supersymmetry. And you will see that we are so lucky in the entire superstring theory, you don't need more than n equal to 2 supersymmetries. For different reasons, the great guys have worked out many things, and I'm just telling you the conclusion that, so you have n equal to 1 superstrings, n equal to 2 superstrings. Okay. By n equal to 2 superstrings, you would just simply, you can look for my simple prescription that you can look for 2 epsilons. If you have only one epsilon or 2 epsilons. Okay. Only one, n equal to 1 supersymmetry. Okay. So, alright, we are lucky right now we work with n equal to 1 supersymmetry, and this is not a function of sigma alpha, this is just a constant spinner. It means that in terms of the conventional terminology of, I would call it global supersymmetry. If my epsilon were a function of sigma alpha, then I would have local supersymmetry. Okay? So local versus global. So we work with global supersymmetry. It's not important, it's not necessary that a theory which is invariant under global gauge symmetry would also be symmetric under local supersymmetry. Maybe not. Okay? Maybe not. So it depends on what kind of theory is. Okay. In our conventional field theory, I can always recap the simplest examples. If you consider the complex scalar field theory that we have discussed a little bit, given by two fields phi and phi star, it is invariant under so-called global phase transformations or global gauge transformations. They are also sometimes called as the gauge transformations of the first kind. And when they are where the gauge parameter is not a function of x nu in field theory of x nu. Here it's not a function of sigma. Alright. And if you consider a theory like when you consider Higgs mechanism, so you consider complex scalar field theory along with the U1 gauge field, electromagnetic field, A mu. Okay. And then that theory, as you can see, is invariant under local gauge symmetry. So the gauge parameter there is a function of x mu. Okay. So just to, my aim always is to connect the advanced ideas and topics with the already well-known simple idea in conventional field theory. Okay. Now we can proceed further. So that's fine. And this, therefore, you see, without this supersymmetry transformations, these are two fields. So this, without this term, this is a free field theory. Without this is a free field theory of fermions. This is a free field theory of bosons. Okay. This is anyway equivalent to 1/2 d mu phi, right? And this is from the same analogous to the Dirac-Lagrangian, okay? But the supersymmetry transformations, they relate the two. So they take bosons to fermions and fermions to. Is this fine? Good. Now we are ready to understand these things further. Let me initially address this little bit more. So let me define let me first introduce because I would prefer to work with the well, in any case, let me first define rho 0 and rho 1. So rho 0 minus 1, 1, 0, and rho 1 I would define as 0, 1, 1, 0. Okay. In fact, in the literature, you will find a multiplicity of the representation of these gamma matrices. These are gamma matrices here because we are dealing with two-dimensional word sheet or super word sheet. So we are denoting them by different names, rho 0, rho 1, and there would be an equivalent of your gamma 5, which is your so rho 3, which is analogous to rho 0, rho 1, you can prove the entire algebra of Dirac algebra of these gamma matrices. Okay, but I should at least give the definitions of rho 0 and rho 1. We would work with this particular representation. Okay, this is called as the Majorana representation. This is called as Majorana representation. In the literature, you can also find. Let me just tell you for short. So here, one thing more that I would define is psi mu bar would be defined as the Dirac conjugate, and this is the Dirac adjoint psi mu dagger times I rho 0. Sometimes I into rho 0 is defined as beta, yet another matrix beta, which is I into iodine rho 0. So this is psi mu bar transpose into some matrix C is psi mu dagger I rho 0, and this is my charge conjugation matrix C is charge conjugation matrix, which is defined as iota into rho 0. And if you have that, then you can see from here psi mu transpose is just simply equal to psi mu dagger, and actually it just amounts to psi mu transpose is equal to psi mu transpose and complex conjugate. So this tells you psi mu bar is psi mu star, and this tells you that psi mu plus minus is psi mu star plus minus. So psi mu is real and its components are so its components are real. Okay, and then you tell me, then I will erase this. Okay. Some authors, they take the definitions of rho 0, in the definitions of rho 0 and rho 1, they take iota here, which means overall multiplied by iota, and this also multiplied by iota here, so overall multiplied by iota. This is just, I have mentioned it, it's enough to work with one convention. But if you are reading, if you happen to read the other, just watch out for the definition of rho 0 and rho 1. Is an iota sitting inside or not? If yes, you can pull it out and accordingly take care of it. Okay? Alright? So, this is how we work with the so-called Majorana representation, and here we don't have this iota.